Now, one last thing that I want to do today is another aspect of space-time curvature that has to do with something very, very fundamental and very interesting. We want to make a model of cosmology. We want to take Einstein's equations and Einstein's theory and this whole thing and apply it somehow to the universe as a whole. Think of the basis of gravitation was the tidal acceleration. What is tidal acceleration? It's really two particles which are in an inertial state, nevertheless experiencing relative acceleration. That's really the essence of space-time curvature and of Newtonian gravity, right? Just like on a curved surface, we have geodesics that can get closer and further in ways that you wouldn't expect of geodesics in a flat space. Similarly, if we consider each one inertial and therefore geodesic world lines, and the world lines are moving towards each other, away from each other, and so on, that's an indication of curvature. We said briefly previous time, that we can also apply that same kind of conceptual thinking to cosmology and think of the universe as a collection of particles. Now, when you say particles, it's an idealization, right? But you can apply it to cosmology, look at the entire universe, take the universe as a bunch of particles. Your particles can be galaxies or clusters of galaxies or whatever it might be. At some scale, you're going to look at the universe and say, I just have a bunch of these particles. It's a bunch of free-fall particles. Now, in theory, therefore, each one can consider itself inertial. However, it's entirely possible, given what we know about gravity, that the collective gravitational effect will be also an anomalous seeming relative motion of these particles. Okay? Now you can't argue a priori this way. What I'm arguing now is kind of post hoc. That's in fact what happens. Basically the phenomenon of gravity. It's this seeming anomalous relative acceleration of two particles which should be inertial. What I did mention very briefly last time is we can talk about cosmology in that context also. Okay? Now, the phenomena that we'll observe will be similar to the phenomena that's observed in gravity, where you have a seemingly anomalous motion between two particles that shouldn't be moving between each other relative to each other in that way. That's how the curvature manifests itself. Now what we do is we apply this cosmologically to the universe as a whole. Even though each neighboring clusters of galaxies feels it's inertial, no motion, nothing, nevertheless two neighboring ones will experience acceleration. And the interpretation of that is that there's space-time curvature. What will happen is the points of space-time will have an anomalous seeming kind of relationship between them. In other words, they'll be kind of moving apart or towards each other. Namely, the space of the universe will be expanding or contracting. Although you wouldn't ordinarily think that spatial expansion has anything to do with gravity, and it doesn't at any reasonable level, it certainly wouldn't have been predicted as an effect of gravity. Nevertheless, if we understand gravity at its most fundamental as being this anomalous relative acceleration, we can apply the same kind of thinking and say, well, here we also have an anomalous relative acceleration, namely the points of space are getting further, so we can see, at least conceptually, why that would also be effect of the same source. The source that gives rise to gravity, namely matter energy, is also the source which gives rise to this effect. Namely, the matter energy of the universe gives rise to the effect that there's this expansion of the space of the universe.